Where did everything come from? This profound question has been at the heart of human curiosity for as long as we can remember. From ancient civilizations gazing up at the night sky to modern scientists peering through powerful telescopes, the quest to understand our origins has driven countless generations. This question has puzzled humans for centuries. Early astronomers and philosophers pondered the cosmos, creating intricate star maps and theories about the heavens. They sought to explain the mysteries of the universe with the limited tools and knowledge they had. The answer, according to modern science, is both simple and mind-boggling. The universe began with the Big Bang. This monumental event, occurring approximately 13.8 billion years ago, marked the birth of everything we know. It was a moment of unimaginable energy and density, setting the stage for the cosmos to unfold. Imagine a tiny speck, smaller than an atom, containing all the energy and matter we see today. This infinitesimal point, often referred to as a singularity, held within it the potential for galaxies, stars, planets, and even life itself. This speck, incredibly hot and dense, exploded outward, creating space and time itself. The Big Bang was not just an explosion in space, it was an explosion of space. As the universe expanded, it cooled, allowing particles to form and eventually coalesce into the complex structures we observe today. This isn't just a guess. The Big Bang theory is supported by a robust framework of scientific evidence. Researchers have spent decades analyzing data, conducting experiments, and refining their models to understand the universe's origins. Scientists have gathered a wealth of evidence supporting the Big Bang theory. One of the most compelling pieces of evidence is the cosmic microwave background radiation, the faint afterglow of the Big Bang which permeates the universe. This evidence comes from observing the universe around us, from the faint afterglow of the Big Bang to the movement of distant galaxies. The expansion of the universe, observed through the redshift of light from galaxies, further corroborates the Big Bang model. By studying these clues, we can piece together the story of our universe's birth and evolution. Each discovery brings us closer to understanding the profound question of where everything came from, revealing the intricate tapestry of the cosmos and our place within it. The Big Bang theory describes how the universe expanded from an extremely hot, dense state. Picture a balloon with dots drawn on it. As you inflate the balloon, the dots move apart. Similarly, the Big Bang wasn't an explosion space, but rather the expansion of space itself. As space expanded, it cooled, allowing matter to form. This expansion continues today. We know this because distant galaxies are moving away from us. The further away a galaxy is, the faster it's receding. This observation, known as redshift, is a key piece of evidence supporting the Big Bang. Imagine a fire that happened long ago. Even though the flames are gone, the heat lingers. Similarly, the Big Bang left behind a faint afterglow, a whisper of its incredible energy. This afterglow is called the cosmic microwave background, or CMB. The CMB is everywhere in the universe. It's incredibly faint, but scientists have built sensitive telescopes to detect it. The CMB tells us about the universe when it was just a few 100,000 years old, a time when the first atoms were forming. When an ambulance passes by, its siren sounds higher pitched as it approaches, then lower pitched as it moves away. This is called the Doppler effect. Light, like sound, travels in waves. Just as sound waves stretch or compress, causing a change in pitch, light waves can also stretch or compress, causing a change in color. When a galaxy is moving away from us, its light waves stretch, shifting towards the red end of the spectrum. This is called redshift. The faster a galaxy is moving away, the greater its redshift. By measuring the redshift of distant galaxies, astronomers confirmed that the universe is indeed expanding. Section 5. The recipe for a universe. Light elements and their abundance. In this section, we will delve into the fascinating story of how the lightest elements in the universe came to be and why their abundance is crucial to our understanding of the cosmos. The Big Bang theory doesn't just explain the expansion of the universe, it also provides a comprehensive framework for understanding the origins of the simplest and most abundant elements in the cosmos. The theory suggests that the universe began as an incredibly hot and dense point, which then expanded rapidly. Among the first elements to form were hydrogen and helium, the lightest and most abundant elements in the universe. These elements are the building blocks of stars and galaxies, and their formation is a key piece of the cosmic puzzle. In the first few minutes after the Big Bang, the universe was a hot, dense soup of protons and neutrons. These subatomic particles were moving at incredible speeds, colliding and interacting in a chaotic dance. As the universe cooled, these particles began to slow down and combine to form the first atomic nuclei. This process, known as Big Bang nucleosynthesis, was responsible for creating the initial abundance of light elements. During this time, conditions were just right for protons and neutrons to fuse together, forming the nuclei of hydrogen, helium, and small amounts of lithium and beryllium. The Big Bang theory predicts the precise amounts of hydrogen, helium, and other light elements that should have formed during this period. These predictions are based on our understanding of nuclear physics and the conditions present in the early universe. Amazingly, these predictions match the observed abundances of these elements in the universe today. Observations made with telescopes and other instruments have confirmed that the amounts of hydrogen and helium we see in the cosmos align perfectly with the amounts predicted by the Big Bang theory. This remarkable agreement provides strong evidence for the Big Bang and helps us understand the fundamental processes that shaped our universe. Section 6. A burst of growth, cosmic inflation. The Big Bang theory is a remarkable success story, but it leaves some questions unanswered. For example, why is the universe so smooth and uniform on large scales? To explain this and other puzzles, physicists proposed a period of incredibly rapid expansion in the first fraction of a second after the Big Bang, called cosmic inflation. During inflation, the universe expanded at an unimaginable rate, much faster than the speed of light. This rapid expansion smoothed out any initial wrinkles in the fabric of space-time, explaining the universe's remarkable uniformity. Section 7. From atoms to galaxies, building the universe. After inflation, the universe continued to expand and cool. As it cooled, quarks, the building blocks of protons and neutrons, combined to form these heavier particles. Protons and neutrons then came together to form the first atomic nuclei, primarily hydrogen and helium. Over millions of years, gravity pulled these atoms together, forming vast clouds of gas. These clouds collapsed under their own gravity, igniting the first stars. Stars in turn grouped together to form galaxies, the building blocks of the large-scale structure we see in the universe today. Section 8. The universe's timeline, a story in stages. The universe's history is often divided into different stages or epochs, each representing a significant phase in its evolution. These stages help us understand the complex processes that have shaped the cosmos over billions of years. The earliest epoch, lasting just a tiny fraction of a second, was a time of extreme energy and temperature, where the fundamental forces of nature were unified. This period, known as the Planck epoch, was characterized by conditions so intense that our current understanding of physics can barely describe them. As the universe cooled, these forces separated, leading to the formation of particles and the eventual dominance of matter over antimatter. This separation marked the end of the grand unification epoch and the beginning of the inflationary epoch, where the universe expanded exponentially in a fraction of a second. The universe then entered the radiation era, dominated by light and other forms of radiation. During this time, the universe was a hot, dense plasma of particles and radiation, and photons were constantly interacting with electrons and protons. As the universe continued to expand and cool, it transitioned into the matter era, where matter became the dominant component. This era saw the formation of neutral atoms, allowing light to travel freely for the first time, leading to the cosmic microwave background radiation we observe today. Within the matter era, we have the formation of stars, galaxies, and eventually planets and life. Stars formed from clouds of gas and dust, igniting nuclear fusion in their cores. Galaxies, vast collections of stars, gas, and dark matter began to take shape. And within these galaxies, planetary systems formed, setting the stage for the emergence of life. Today, we live in what is known as the dark energy-dominated era. Dark energy, a mysterious force driving the accelerated expansion of the universe, now plays a crucial role in its evolution. The future of the universe remains uncertain, but by studying its past, we gain insights into the forces that have shaped it and the possible scenarios that lie ahead. Section 9. Mysteries of the Cosmos. What we still don't know. While the Big Bang Theory provides a compelling explanation for the origin and evolution of the universe, there are still many unanswered questions. What is dark matter, the mysterious substance that makes up the majority of the universe's mass? What is dark energy, the even more mysterious force driving the universe's accelerating expansion? These are just a few of the many mysteries that continue to intrigue cosmologists. The quest to understand the universe's origins is far from over. With new telescopes and experiments, we can peer deeper into the cosmos and unravel the secrets of our universe's birth